Uh, Good morning, everyone. Can you guys confirm if you guys are hearing me clearly?
Yeah.
Okay, I want to welcome everyone to my lecture today. Today, February 3, I'm actually going to be walking you through another fascinating topic in statistics. But you know what? Um, I'll first finish the material for Friday. The material for Monday before I actually go to today's material. You remember on Monday, uh, we use this particular material. We started something on Bayes' theorem. But you know what? Today, I'm actually uh, going to walk you through application of Bayes in real life practical situation. Okay, so that is what I have for you before I will now go into today's material. So I'm going to quickly take you to where we stopped the other time. Give me 1 second. Now the other time we actually stopped at this example, okay, and I'm going to continue from here before I go into today's material. Now, this example we were on this example on Monday before my time, so actually go home. So I want to solve one or more example from popular topic known as COVID-19. As you know, COVID-19 tests are common nowadays. Okay, but some result tests are not, you know, they are not true. Let's assume a diagnostic test has 99% accuracy and 60% of all people have COVID-19. If a patient tests positive, what is the probability that they actually have the disease? Now, let me tell you, in medical diagnosis, uh, because the efficiency of machine used in diagnosis is not 100%, therefore there's possibility of, uh, wrong diagnosis. Okay, so there's something that we call sensitivity. Okay, give me 1 second. I'm actually going to write that down. Okay, so there's something that we call sensitivity. Okay, there's something that we call sensitivity, and there's something that we call specificity. Can you guys confirm if you guys are seeing what I just wrote right now? Can you see what I wrote? Sensitivity. Okay.
Yep.
Now, what is sensitivity? Sensitivity is the ability of a test to actually, to correctly identify uh, those who have the disease. Okay. So, which means with the machine, those who have disease needed to be tested positive. It is not all the time that this happen. So therefore, we may want to find the probability, okay, of that, okay, because it is not all the time, there's possibility that, you know, some may have the disease and the test and the machine may not be able to identify them to have to have the disease. And that's what we call specificity. Okay. The specificity, on the other hand, is actually the probability, okay, to identify those who do not have the disease. Okay, it means they have to test negative to the machine if they do not really have the disease. It is not all the time that this happen, and that is why you know it raises a probability question. Now, what am I trying to talk about in general for sensitivity is that, you know, the ability of the test to, to pick what you are looking for. I'm going to say that again. Sensitivity, in another word, in another definition, ability of, you know, of the test to pick up what you're looking for. We're looking for the people that actually have COVID. Okay. What is the ability of our machine to be able to pick them? Because we know that it is not, all the time that this happen. The machine may not be able to pick all of them. So what is the ability of the machine or testing equipment to pick up, what you're looking for? And for the specificity, okay, it is the ability of the test to reject what you are not looking for. I'm going to say that again. The ability of the test to reject what you are not looking for. Why sensitivity? Ability of the test to pick up what you're looking for. Okay? So that is why we actually want to consider um, this example. Okay, so in this example, you have been told we actually want to see how Bayes theorems can be applied. Okay, you are already been told that 60%, okay, of all people have COVID-19 according to this question. Okay, and the diagnostic test does not have 100% accuracy. It only has 99. Take a look at that. Now, if a patient tests positive, okay, a patient has tested positive, what is the probability that they actually have the disease? You know, this question cannot be answered directly because this particular question here is posterior. It's a conditional probability, but this is posterior. It cannot be answered directly unless you pass through the likelihood. Okay? So if a patient tests positive, what is the probability that they actually have the disease? Now, this is what you're going to do. You've been given that 60%. Okay? You need to first consider 100 units. You've got to take on 60%. Okay? How many of the 100 we got the disease? Okay? According to as reported, you multiply 100 by 0.6, which is going to give you 60. Automatically, it means 40 out of 100 do not have COVID. Okay? And that's why I call this COVID-19 and not COVID. Okay? Based on 60% that have the COVID, of course, it means based on 100 units, um, 60 out of 100 we got the COVID. Okay? And 40 out of 100 will not have the COVID. Now, uh, there's what we call that we can have error in diagnosis. Okay, we have, and I'm actually going to let you see that right now. Now, take a look at this. How, we want to figure out what is we mean by true diagnosed positive. The true diagnosed positive is actually, the probability that we're talking about, that correctly identify those who have the disease. Of course, they have to be positive, you know, during the test if they duly have the disease. Now take a look at this. The number that have the disease, okay, multiplied by 0.99, which is the probability, which is the accuracy of the machine. You know, uh, we have 59.4. 59.4 is less than 60. Okay, if the machine were to be 100% efficient, of course, the machine should be able to correctly identify all the 60. But right now, the machine is not correctly identify all the 60. Take a look at that. The machine is only identify 59.4 out of 60. Okay, which we call the true diagnosed positive. Now, since this is not up to the number of people that have it, okay, then it means we're actually gonna have a false diagnose. Okay, a false diagnose is actually going to be use the number that have it, 60, that nature knows they got a disease, multiply by the error. Of course, how do I get a 0.01? Of course, 1 minus 0.99. 0.01 here is just 1%, because 1% of the time, that machine will not correctly pick those who have the disease. Therefore, in terms of number, those the first diagnosed, okay, the first diagnosed, okay, they have the disease, okay, but the machine, did not actually turn them out to be positive. The machine probably actually turned them to be negative. This is it. Okay, so that is a zero point 0.6, but 59.4 right here, they got the disease and the machine correctly identify them. Okay, that's 59.4. Okay, now let's go to the not COVID side. We've just talked about COVID side. Okay, let's go to the not COVID side. Okay, in the not COVID side, nature knows the truth. How many of the people do not have COVID? 40. Okay, nature knows the truth. 40 do not have COVID. Okay, now if 40 do not have COVID, okay, if I multiply 40 by 0.99, which is the accuracy of the machine, it's actually going to give us 39.6. Of course, if the machine is 100% efficient, we were supposed to have 40. The machine is supposed to correctly identify all the 40 to be negative, okay, because they don't really have COVID. But based on what we are seeing right now, the machine is not going to identify all of them, okay? Therefore, we're going to have a false diagnosis. Or year two. Of course, the false diagnosis is going to be 40 multiplied by 0.01, and that will give us a zero point 0.4. Now, take a look at that. Here and here, we're referring to this as a correct diagnosis. I'm going to say that again. And that's how we call them true diagnose. Okay? Now you can see that now. And when you take a look at this guy here and this guy here, that is the error. Okay? That is the error that we're talking about. But you know what? If we now want to obtain the correct diagnosis, I mentioned here that this guy here, okay, these are the true diagnoses. Can you see that now? Okay, and then this guy here, these are the false. Now, if I'm interested in the total unit which have positive, okay, the total unit which has positive, you could have positive results, and you may have it, you may not have it. I'm going to say that again. Where does positive result occur? The positive result occur here. The positive result actually here, people really have the disease. Okay. Another positive result occur here. But you know what? The positive result that occur here, you know, they did not have the disease. So the machine could dictate you to be positive. Okay. It can occur in two ways. It's either you truly have the disease or you do not. Okay, it's either you truly have the disease or you do not. Now, when you add 59.4 to 0.4, that is why we have 59.8. I want you to take note of that. We're talking about right now, we're talking about positive results. Okay, the positive result right now actually represent total probability. You remember last week I talked about on Monday I talked about total probability. Take a look at that. That is total probability that you're applying right here. Okay, in the total probability, you're actually adding that to that. In the total probability, you are interested in positive results. The positive result, those people may have it and they may not have it. Okay, and that is what we're adding together here. Take a look at that. Okay, but you know what? Out of this total right here, out of the total positive right here, the true one is the 59.4. That is a true positive. Okay, that is what we mean by true positive. Okay, so I want you to take note of that. If you now want to find the probability now of correctly identify those who have the disease, you know what you're going to do? Then you can actually, how do I got this guy here? Of course, if you try 59.4 divided by 59.8, okay? 59.4 divided by 59.8, okay? then you're actually going to have 99.3%. Okay, if I want to use Bayes, can you guys confirm if you guys are still hearing me clearly?
Yes.
We
Okay,
can hear you.
thank you so much. The reason uh, why I'm stressing more on Baye, because the assignment for next week is actually going to center mostly on Bayes and whatever we're doing this week. And that is why I'm repeating this. I want you to really understand, uh, what a Bayes is all about. Now, uh, some of you, I think I received some messages from you guys, which I actually want to talk about here. Take a look at this guy here and this guy here. They are not the same. Okay? It's just like probability of A intersection B, I mean A giving B, and the probability of B giving A. Okay? And I want to explain the difference between them, okay, using this COVID-19 results. Now, let me start with this. What is the meaning of this? This is actually what we want to solve. This is what we're looking for. That is the posterior. Okay? This guy here is the posterior. Okay? This guy here is a likelihood. Okay? That guy is a likelihood. And this guy here is a prior. Okay? That guy here is a prior. Now let's take a look at, let me start with the posterior. What do I mean by that? The probability, okay? You know, let me just explain this. Somebody has tested positive for COVID, okay? What is the probability that COVID-19 is actually present? I'm going to say that again. I'm trying to interpret this posterior right now. Somebody has already tested positive for COVID, okay? And we actually want to figure out what is the probability that disease is present. That is what we mean by this. That is the posterior that we want to carry out, because we call it posterior because the machine has already done the job. That is post analysis. You have already used the machine. The machine has done the job. Okay. Now, that is how to interpret the probability of COVID-19 giving positive. Look at that. Positive has come first. Okay. Positive, this guy here has already come first. The machine has already, you know, this particular person has already tested positive to the machine. Now, what we want to do, what is the probability that the disease is actually present? That's what we want to do. And that is how interpreted. Now, let me now go to the likelihood. This guy here that I call likelihood. Okay. How is this interpreted? Okay. Now, this is interpreted as you got a COVID, somebody have a COVID. What is the probability that the machine, okay, will be able to detect that? Oh my God, that is different from this. They are not the same. Okay, you guys see here, enemy?
Yeah.
Okay,
Yes.
Yes.
okay. What I'm explaining right now, the disease is present. The nature, because the nature knows the truth. The disease, the COVID-19 is actually present in the patient, but you know what? What is the probability that if this patient with COVID-19 go for a test, what is the probability that the machine will correctly detect that? That is what we mean by this, which is a likelihood. And that we call it likelihood, we call it data, because it is the machine that will determine that. Where am I trying to stress more on this? I'm trying to differentiate between the two. They are not the same. They are not the same at all. They are not. Okay? Now, what I'm trying to talk about right here, if the machine now says something, okay, we got this one from the machine, which is the likelihood that I talk about, okay, and this guy here is the probability of having COVID-19 in the first place, okay. So this is going to be prior, even before the person is selected, it is being tested. We got it. We know the probability of having COVID-19. Okay, That's a prior. Okay, combining the prior with the likelihood, of course, that way actually going to give us posterior. Take a look at that. Posterior. So please, there's a difference between the two. Okay, now we now want to apply this to the question, to the same question. Okay, now the 0.99, initially you were given that, we're told that the machine is 99% accurate. Oh my God, what you are given is the likelihood. Okay, what you are actually giving is a likelihood. I'm actually going to take you back. Okay, I'm going to take you back to where the statement, take a look at that. Is this guy here? Okay, diagnosis text has 99% accuracy. 99% accuracy means, okay, 99 out of 100 time, of course, it's actually going to correctly identify, the patient. Okay, whether they have the disease, though if they have the disease, 99% of the time it will correctly identify them. If they do not have the disease, 99% of the time it's actually going to identify them. Now take a look at what I have right now, and that is why I'm calling this guy the probability of the positive given COVID-19. Okay, the COVID-19 is present already. What is the probability that the machine, okay, we actually correctly identify, okay, the patient. Okay, this is likelihood. Take a look at that, where they're able to arrive at 99% because they've used that machine over time and they've realized its accuracy. That is why it is likelihood. Take a look at that. Then we're told that 60% of the people have the COVID. That's a prior. That is, the probability of COVID-19 is a zero point 0.6. Okay, now the probability of the positive right here is actually going to be total probability. Of course, in Bayes' theorem, okay, in Bayes' theorem, we normally have the denominator, right? The denominator is actually going to be the probability of being positive. And don't forget the other time, the probability of being positive can occur in two ways. The probability of being positive can occur in two ways. Okay, the first way, you could test positive when the disease is present. Okay, and you could also test positive when the disease is absent. Okay, so that is why we call that the probability of positive, which is also called the total probability. Okay, so then I'm actually going to go into the formula right now, which means the posterior that I'm looking for, the probability of the COVID-19 giving positive, okay, will actually be equal to this. Okay, what am I using right now? I'm trying to use the probability of the positive, okay, giving COVID-19, okay, multiplied by the probability of COVID, okay, and divided by the probability of the positive, okay, which is the total probability. Okay, that's exactly what I put right here, and that actually gave me a 0.993. Okay, so with Bayes' theorem, if you apply Bayes' theorem, we got a 0.993. Okay, if you did not apply Bayes' theorem, let me take you back. Okay, we got a result the other time. Oh my God, look at that. We got this the other time when we did not apply Bayes' theorem. We still got the same result. How do we get a 0.993 right here? Oh my God, you're gonna do 59.4 divided by 59.8. Of course, the 59.4, of course, that is a number that were correctly identified out of the two number. Take a look at that are positive. Okay, that still give us that. Okay, so I just wanted to take note of that even using a different formula or other than Bayes' theorem, you're still going to get the same results. Okay, because of that, I actually want to tell you this today. In the clinical epidemiology screening, we normally have errors. Okay, we normally have errors. We've seen situation whereby some people did not have COVID and the machine says they have COVID. And we've seen situation whereby, some people actually have COVID, but the machine was not able to detect them. Can you guys confirm if you guys start still hearing me clearly?
Yes.
Okay, thank you so much. Thank you for confirming that. I just wanted to, if you are not, or enjoying my statistical party, please reach out to me. Okay, just want to make sure everybody is fine. Okay, are you guys good? Are
Yes.
okay? Thank you so much. Thank you for confirming that. Oh my God, this guy they are joining my party. Okay, good job. Okay, now take a look at what I have right now. Then I put up a table right here. Okay, I'm actually gonna call that a table. Take a look at that. Okay, now when disease is present, okay, and then if the machine tests, if the patient actually tests positive, okay, we're gonna call that true positive, true positive, okay, and the number of that is A. Okay, if the disease is absent, okay, and the machines, actually, the patient tests positive, that is a false positive, false one. It's not a good one. It's a false positive, and we use B to represent that. Okay, if the disease is absent, okay, I mean it's present. Look at that, and the patient tests negative, and the disease is present, but the patient tests negative. That's a false negative. We're gonna refer to that as C. Okay, and lastly, the disease is absent. Okay, and the patient, the machine, the patient tests negative. That's a true negative. Now, when you take a look at this guy here, okay, that's exactly what we want. That would be a correct decision. A and D, true positive, true negative. But you know what? The bad decision is actually going to be this guy here. Okay. Now, in the next test, I mean, in the next assignment, I can ask you to find the sensitivity and specificity. Don't forget, I said by sensitivity, the what is the ability of the test, okay, to pick what we're looking for. Ability of the test to pick what we're looking for. And of course, that would be A divided by what is the total here? You know, the total number of people that have the disease is A plus C. Okay, what is the probability that you're actually going to have a correct diagnosis? That's going to be A over A plus C. Okay, another here, the number of people that who do not have the disease is B plus D. Okay, what is the probability? Okay, of a true negative? The probability of a true negative is the same thing as specificity, while the probability of a true positive is sensitivity. Okay, don't forget I said sensitivity is the ability of the test to pick what we're looking for, and why specificity is the ability of the test to reject what we're not looking for. Does that make sense to everyone? Okay, I want to go into another. If you take a look at before I go to today's topic, I actually want to apply Bayes' theorem in the court of law. Oh my God, we want to leave hospital right now. Okay, we want to leave medical application right now, and I actually want to take you to, um, the in law practice. Okay, do we use Bayes' theorem in law practice? And I want to tell you, uh, you know, Bayes' theorem has been used in court in litigation to settle court cases where the knowledge of Bayes' theorem put forward by Thomas Bayes 1759 was actually used to analyze evidence before the courts. Okay, we are in court right now. Okay, we're in court right now. Okay, now I'm actually going to share my whiteboard and I will need you to confirm if you are seeing my whiteboard. Can you guys confirm if you guys are seeing my whiteboard?
Yes.
Yeah.
Thank you so much. We're going into the court of law right now. We're going into the court of law. Now, take a look at this. Um, Somebody was accused. Okay. We have a defendant right here. Okay. You know, we have a defendant, we have a person that was actually accused of probably participating in a crime. Okay. Now, the reason why this defendant was actually accused is because the the blood type, okay, the blood sample found on the crime scene actually matches the blood type of the defendant. Okay, that was why this defendant was accused of that wrongdoing. Okay, now let me tell you this. I under the law, give me 1 second. We have two hypotheses under the law right here. The non-hypothesis is actually going to assume the defendant, defendant, the defendant is innocent. Okay, alternative. Okay, the defendant. Okay, the defendant. Okay, is guilty. Okay, now these are the two hypotheses before the court of law. Okay, like I said, right now we are applying our Bayes theorem, the Bayes rule, okay, in law. That's what we're doing right now. And the non-hypothesis actually, uh, you know, an accused person, according to the Constitution, uh, is is being, is deemed to be innocent until the court of law prove otherwise. Okay. Now, it means I have an event I. Okay. The event I means the defendant. Okay. The defendant. Okay, is innocent. Okay, that is event I. The defendant is innocent. Now, and we want to, what is the probability? Okay, so P into I will be the probability. Okay, the probability that the defendant is innocent. The probability, the probability that defendant, okay, defendant, okay, is innocent. Okay, and you know what? The probability that defendant is innocent is actually going to be a prior probability, because right now we've not used evidence for now. Okay, the probability that defendant is innocent is P into I, which is a prior probability. Okay, and maybe probably they could look into the defendant record. Does he have history of stuff, something like that? Okay, and that is why you need to cherish your record a lot, and that's why we need to obey the law all the time. Okay, you need to obey the police all the time. Okay, so because whatever we do actually go into record. Okay, can you guys confirm if you guys are still hearing me clearly?
Yes.
Okay, thanks for confirming that. Now, we have the probability of I, which is the probability that the defendant is innocent. Okay, but you know what? What this particular court is looking for, the particular court is looking for this. I'm gonna write that now. The court is actually. Give me 1 second. I'm gonna clean my board right now. Because I want you to understand this, and that now what we know right now is the probability that the defendant is innocent. Okay, now this is what the court is actually looking for: the probability of this given this. Take a look at that. This is posterior. This is what the court is looking for. The court is looking for what is the probability, okay, given the evidence we have. Okay, given the evidence we have, what is the probability that an accused person is innocent? I wanted to take, this is what the court is looking for. The probability, I'm going to write that, probability, okay, the probability, okay, that, you know, an accused person, okay, an accused person, okay, is innocent, okay, is innocent, okay, given given the evidence, okay, given the evidence before the court of law, okay. So this is what the court is looking for, which we call the posterior probability. Okay, there's a posterior probability. But let me tell you this question cannot be answered directly. Okay, this question cannot be answered directly. Okay, now we need likelihood. Okay, we need likelihood, and I'm going to write the likelihood for you right now. Give me 1 second. You're going to see the likelihood. I'm actually going to write the likelihood for you right now. Now, this is the likelihood I talk about, the probability of E given I. Now, this is the likelihood. Now, I want to tell you the difference between the two. Okay, the two of them, they are not the same. Now, this guy here is saying, after seeing the evidence, okay, what is the probability that the accused person is innocent? Okay, the probability that accused person is innocent after seeing the evidence. This is different from this guy here. Okay, now it means what I've been able to write out for you. What we know right now, we know the prior probability. Okay, the prior probability is the probability that accused person is innocent. That's a prior. They could be able to they could be able to figure that one out, maybe probably um using the past record of the person. Okay, now this is a prior probability, but the likelihood right here, of course, the reason why the accused person, why this person was alleged in the first place is because, according to the forensic analysis that was conducted, okay, the blood sample found on the crime scene matches the blood type of the defendant. And that was the reason why it was alleged in the first place. Now, the question now is, since the evidence is matching blood type, and in every 1 out of 10 people, okay, if that occur, now what I'm going to do now, I want to start assigning figure now. I want to assign a figure to this. Okay, now take a look at what I'm trying to write right now. The probability of the fact of probably that this guy is innocent, maybe it is 0.4. I'm just assuming. Okay, how did they get 0.4? Maybe probably from past record. Okay, now the probability after seeing the evidence, okay, the probability after seeing the evidence, the probability that the accused person is innocent, let's say it is 0.1. Why do I get a 0.1? Maybe after forensic analysis, they realize that 1 out of 10, 1 out of every 10 people, okay, that we have their, what is it called? Yeah, their blood type matches, okay, the one on the crime scene. Okay, now this is a probability, this is likelihood right here. Okay, this guy here is a likelihood. Okay, this is a likelihood. Okay, this is based on the result of forensic analysis, and this guy here is a prior. Okay, and you know what are we looking for? We are actually looking for the probability. We're looking for this, okay, which is a posterior, the probability that an accused person is innocent, okay, given the evidence before the court of law. Now, take a look at this. If I want to apply the Bayes theorem right now, I'm actually going to have this, okay, the probability of this divided by the probability of this, okay, this, okay, plus the probability, okay, of this given complement of that, then I complement. And I'm going to, what I have here now is the total probability. Now, let me explain that to you. Okay. What I'm trying to talk about right here. Okay. This guy here is the likelihood that I talk about. This is the prior. Okay. You have the values for them, right? This guy here, how am I going to interpret this guy? This is a probability. Okay. That the evidence, what is the probability that given that the accused person is guilty? Okay, what is the probability of the evidence? Of course, the probability of the evidence, because guilty here is the complement of innocent. The complement of innocent is guilty. Okay, and I'm going to assign 1 to this. We normally assign 1 to that because when the accused person is guilty, okay? And with the evidence, of course, we normally is going to assign one, we know assign one as a probability. Okay, now this is a zero point 0.4, this is a zero point 0.1. So this guy here is a zero point 0.1, this guy here is a zero point 0.4, okay? This guy here is 0.4, and this guy here is 1. Then what is this guy here? The probability of the complement. Then you're going to subtract the zero point 0.4 from 1. That is going to be 0.6. Okay? So when you do that at the end of the day, uh, you're going to have 0.0625. Okay? You're actually going to have, so which means what you want to find, take a look at what you are trying to find right now. Okay, what I'm trying to talk about, the probability of I given A is equal to is zero point 0.1 into 0.4 divided by 0.1 is 0.4. Okay, then plus 1 multiplied by is 0.6. Okay, can somebody figure out this one? That will be 0. So what do we have? So we're gonna have let me clean this to have a room. So you're actually gonna have is 0.04 divided by 0.04 plus 0.6. So which is 0.04 divided by 0.64. Okay, this is more or less looking like 4 over 64, which is 1 over 16. Can somebody give me that? What is 1 over 16? What is 1 over 16? Let me use my calculator right here. One over, are you guys still hearing me?
Yeah.
Okay, so 1 over 16 is going to be 0.0625. Okay, it's 0.0625. Now, if you take a look at this has a significant impact on this case, because this probability is so small. And what are we finding? The probability that after seeing the evidence, giving the evidence, the probability that the accused person is innocent. And look at that probability is very, very small. So which means an accused person is not likely to be innocent. Okay? Based on what we see right now, because this will significantly impact this case. Is there anyone who want to ask question before I go to the to what we have, what I have for you today? Is there anyone?
Yeah, I thought Bayes' theorem was like on the bottom was just the probability of being innocent.
Oh no, it is not the oh, you mean the no, it is the probability of the evidence.
Uh-huh.
Look at that. You could have evidence when accused person is guilty. And you could also have evidence when it is innocent. You could also have evidence when it is guilty. Does that make sense?
So is this not like Bayes' theorem? Or because
It
the
it is it
formula was
okay.
oh, sorry about that.
Did you see that now?
No, I was because like I thought the formula for Bayes' theorem was supposed to be like P probability of I on the bottom. Why do you have to like do the complement and stuff?
Okay, now let me tell you this. Uh, do you know that the denominator is a total probability, right?
Oh, that represents the total probability?
Yeah, in Bayes' theorem, the denominator is always total probability.
Okay, I got you. Thank you.
Okay, you're welcome. Now, what I'm trying to tell you guys now, everything at the bottom here means probability of evidence, okay, which is a total probability, okay? So I want you to take note of that. There is one pattern that I want you guys to see again, that you will seriously understand what I'm trying to talk about. Now, take a look at this. If I write this one, probability of I given E, if I cross multiply, it means I'm multiplying it by probability of E, okay, equal to this guy here. The probability of E given I, then the probability of I. Look at that. Can you see that now? That's what we're doing. Okay. So this guy here, look at that, and look at that one here. Okay. So now, let me read my chart. I think something came in right now. I'm going to stop my, give me 1 second. I'm going to look at my chart. Somebody said, why do we add the probability of the complement? I think I've answered that. The denominator of the Bayes theorem is a total probability. Okay. So the first part is talking about this. Okay, what is the probability of the evidence when an accused person is innocent? What is the probability of the evidence when the accused person is guilty? Okay. Of course, where you're always going to find evidence. When you find evidence, there's possibility you find evidence when an accused person is innocent, and there's possibility you find evidence when it is not. Okay, and that's why I call that total probability. Okay, now somebody said just probability of oh, okay, I think the person was just trying to. Now this is the end of Bayes' theorem. Like I said, the assignments next week will actually dominate Bayes' theorem, sensitivity, and specificity. So please watch out.